Okay, we talked about IR spectroscopy before the test, and we talked about mass spectrometry and how they're used to work out the structures of organic compounds. What we're doing now is going into a lot more detail by talking about NMR spectroscopy, which is a particularly useful technique for us as organic chemists because we can see hydrogens and we can see carbons. We're going to see spectra which are way more complicated than the ones you saw so far, and then for the next exam and the final and what have you, we have to put it all together to be able to solve problems. You're not going to see any more a simple IR and what's the compound. You're going to be given a formula and you're going to be given 5 spectra and you're not given any pictures. You have to decide what it is, and that's particularly difficult and particularly challenging. So what we talk about now is NMR spectroscopy. Again, it's the same technique as MRI. We have these instruments in chemistry if you'd like to come see them at some point. They're quite interesting and they're invaluable. It's all based on magnetism, the idea that nuclei are magnetic, or some nuclei are magnetic, and fortunately for us, carbon-13 and hydrogen-1 are both magnetic, and so they work in this technique. And if you think about the orientation of these nuclei inside of a magnet, if you don't have a big magnetic field outside, you're going to see these things randomly all over the place. But if you do have a large magnet, like we have the can on the pictures that we showed you, you'll see that these things line up, and they either line up with or against the field. And what we're going to see is basically the promotion of nuclei that are against the field, or with the field I should say, to against the field. You're going to see elevation from an E1 to an E2, and we're going to measure that gap. Now fortunately the gap is different for each type of proton. And what we started doing the other day was talking about the basics of the instrument. There's nothing too tricky there. The idea that you need solvents that are blank. In the IR spectrum you use a salt plate which is blank to the infrared, and now we're going to use a solvent in the NMR spectrum that is blank to the NMR. So we use a deuterated solvent. You'll see CdCl3 is often a popular one. So we're going to see a lot of these things. The idea that D does not have this magnetic property, and so it does not show up. If you used CHCl3, it would swamp out the spectrum because the solvent is typically there in great excess, and it would swamp out the spectrum. So we use these blind or these blank types of materials, and we'll see later on that D2O is very useful. We'll start using it with organometallics. We'll start quenching things with D2O, and that will give us an idea of where the chemistry happened based on a labeling experiment. So this is important stuff. The spectrum, typically, that's a complicated spectrum. You won't see anything quite as complicated as that in the class, and you won't have to interpret anything quite as complicated as that. But you can see now a lot more detail, a lot more shape to the structures, a lot more shape to the signals, and you'll see now the gaps between the signals mean something, and the size of the signals means something on top of where they are. It's a very reliable subject, very much like IR. IR told you about functional groups. This technique now is going to tell you about nuclei, C and H for the most part. We looked at this very briefly on Friday, on Wednesday last week, where we talked about equivalence, magnetic equivalence or chemical equivalence. Symmetry is important here. If you're okay with the symmetry ideas from the first term, this isn't any more difficult than that. We should recognize now that we have a methyl group at the end, which is the same as that methyl group through symmetry, and they are one type of proton. Whereas this CH2 group in the middle, it's chemically different because it's secondary, and now we're going to say it's magnetically different. It's in a different environment because it's surrounded by different types of atoms. This is up to you, I think. If you don't get this, come and ask. It's fairly straightforward, symmetry being important. The relationship between the protons at the top here, this is the same as this because this molecule is completely symmetrical. Whereas if you start changing things and you think about moving on from that, if you remove one of these H's and replace it with a D, you can tell they're the same molecule because you turn it upside down, it's the same thing. But if you move on to protons that are not identical when you do this test, that becomes more complicated. So in these examples, we have what we call enantiotropic hydrogens, and because enantiomers have the same properties, they'll typically show in this NMR spectrum at the same place. And it gets much more interesting and more complicated when you get diastereomeric, because just like with the chirality stuff last year, if you had diastereomers, they had different properties. If you had enantiomers, they had the same properties, and that extends itself into the spectroscopy. So we will see compounds like this in the near future, and you'll recognize that they should have different signals because they're in different environments. So I've been using this word environment. It's a lot of what we'll do today is work out the environment of a proton and decide what that does to where it shows and what shape it is. We need some definitions. We need some axes. We don't really talk about the y-axis for this. We'll talk about the area under the curves. That'll be something very important to us. But we're very, very important, we're very interested in something called chemical shift. Where we used wave numbers in the IR, we're using chemical shift in the NMR. This is now the x-axis, and these numbers will be important, and these numbers are on that sheet that you're able to use. So those numbers will be the same if we standardize this thing. And this chemical shift is basically the equation as it says right there. Because we have different size spectrometers, we've got 400, Sammy here might have an 800 in his basement. We need to have the numbers the same to make this thing uniform. So we can see here position of signal minus position of TMS peak at 10 to the 6 times 10 to the 6 divided by the spectrometer frequency. You won't need to do that calculation. All it is very much like alpha D when we did that a while back. It's a standardization to talk about the same numbers using different instruments. Now, TMS. You do need to know what TMS is. It's very similar. You've already seen TMS, right? What was TMS? What was OTMS? Trimethylsilyl. Well, this TMS doesn't have any oxygen right there. It has 4 methyl groups on a central silicon. It's a very simple compound. It's cheap. And it just so happens that the signals for those methyl groups show up at a very convenient place that we call 0. Everything is standardized to that number. All right, so that is our 0. It's to the right-hand side of the spectrum, and everything else we talk about will have a chemical shift relative to it. So today's all about getting the geography out of the way, getting the idea of what the spectrum looks like, so that Wednesday and Friday we can talk about particulars and a lot of detail here and how to use this. So our numbers here are going to be in the 10 to 12 parts per million. If you think about where the million comes from, it's to do with the size of the frequency, size of the instruments we're using. We'll call these 0 to 12 parts per million on the spectrum. So the x-axis is chemical shift measured in parts per million. Everybody all right? Good weekend? No snow? Lots of ice? Yeah, great. Okay, there's a typical spectrum. You will be expected to draw these things and to be able to analyze them to come up with a structure. And again, from now on, you won't be given any pictures. Your job is to actually come up with the actual pictures, the actual structures. We have some nomenclature right there. We've got something called a downfield shift and something called an upfield shift. And if you were looking for TMS, it would be right here. That's where the TMS signal will show, and everything else is measured to it. It's a nice organic soluble material, so it dissolves in the solvents I showed you, and that's useful. So we would say that this signal is downfield of TMS. This signal is downfield of the one to the right, whereas this signal is upfield of this signal down here. As you get familiar with this, the NMR, the sheet will become important, the spectroscopy sheet will become important again, because now we're talking about the top of that sheet, which is very much more complicated than the IR we did. Those chemical shifts are reliable. If you see signals down here, they are probably not simple alkyl groups. And if you see signals up here, it's probably not a benzene ring. So they have definite places they show up, and that becomes very useful for us to be able to analyze and use in problem solving. So there's the sheet. If you have the sheet with you, get it out. And we will start looking at some chemical shifts. Where do the different signals show, and why? And then once we've decided where things show, we can talk about their shape, we can talk about their size, and then we can put it all together and solve some problems. So this is pretty straightforward. You look at an MRI output. An MRI output is way more complicated than this. So if you can manage this, maybe you can handle that stuff, but not the other way around. In this example here, we're looking at the different chemical shifts. So again, that word approximate at the top is important. It means that those are ranges in which those types of proton typically show. Now, we cannot possibly cover every single organic molecule that is out there. So occasionally, you might see a proton that's outside of that range. But if we do this properly, and you practice and I present this properly, you should be able to handle why that happens. Why is a signal showing 2.2 ppm further downfield than I expect it? And chances are it's because there's something close by that's electron withdrawing. Okay, so all those ideas will be useful here. So I've got some definitions here just to go through this. This is important, and people will miss this if they're not careful. Simple alkyl groups. The proton on the simple alkyl group will show to the top right of the spectrum, 0.9 to 1.8 ppm. Why such a broad range? Well, T-butyl, propyl, ethyl, they're all different. And they all have different magnetic environments because they're all surrounded by different numbers of atoms. Allylic, 1.6 to 2.6. I'm not going to go through all of these. Some of them are fairly obvious. But now I'm trying to define where these things will show up. Alpha to a carbonyl. That's something that causes people problems. What does that mean? Write this down. It means protons next to a carbonyl. This is the alpha position right here. Protons next to a carbonyl show at about 2.1 to 2.5 on that scale. And that will be very useful when we start deciding, is it a ketone, is it an aldehyde? And we have to differentiate between similar looking structures. So then we've got alpha to Cn, the same idea, next to a C triple bond N. An alkyne proton, 2.5. That's always helpful. If you had the infrared spectrum as well, you put the two together, you can tell it's an alkyne because you have similar or simple numbers to look for. Benzylic next to a benzene ring, 2.3 to 2.8. Over the next 5 days, getting ready for the next homework, you will be looking at these things and scratching your head and wondering in 2 or 3 or 4 different directions. How do I draw the spectrum of this molecule I've been given? Or, given a molecule, what do I expect? Or given a spectrum, what is the molecule? Given a formula, given all the data. This is not easy at all. For those of you who are getting above my 60 pass rate, this will be fine. Just keep on doing what you're doing. More practice should be fine. For those of you who are not, this is going to be nigh on impossible. Alkene protons, for some reason, show down around 5. Do not memorize these numbers, but get familiar with going backwards and forwards to be able to pick them out. This is way more complicated than the IR stuff we did. Aromatic, now we've got to be careful here, protons are not aromatic, but protons on aromatic rings show around 7 every time. That often will be the first thing you look for. In the infrared spectrum, often you look for a hydroxyl or a carbonyl. They are the first things you look for to get you started on a problem. Often here you're looking for a benzene ring down at 7. That might be the first thing you check to be able to get started. Next to, not next to, but on an aldehyde, this is different now. This is not alpha, this is on the aldehyde. This thing is way downfield, between 9 and 10. And the answers here will all be to do with electron density. Where is the electron density relative to the atoms? And if you go from a ketone to an aldehyde, you might say, okay, the proton here is actually directly on the carbonyl. That carbonyl is very positive. That will de-shield for reasons we'll talk about in a second. And that then gives you this chemical shift, which is way downfield. So this will all be logical. It's up to you to keep up with it. N neighbor, same sort of idea. If you have a nitrogen in a molecule and a carbon next to it with a proton, you're looking around 2.5-ish. If you put a chlorine on a molecule, 3.1 to 4.1. Bromine has an effect, 2.7. And you'll see something general. The more electronegative piece is added, the further downfield it goes. You'll see that as being a general type of idea. O neighbor, I want to point this out so I get it out of the way now. This is a system like this, where you have maybe an ether or an alcohol. Those protons next to the OH group are O neighbors, because they have, guess what, an O neighbor. So make sure you get those two quickly, the alpha carbonyl and the O neighbor. Make sure you understand the difference so this doesn't get overwhelming. Amines are a little bit different. Amines 1 to 3 is a broad range, and you'll see that OH groups typically are unreliable. We'll see why in a second, partly because they're acidic. We'll see here that alcohol is very broad range, 0.5 to 5, and that's often not a useful indicator of the fact that you have an alcohol. What's a better indicator? IR spectrum, signal around 3300, that will tell you have an IR spectrum. You have an OH group, so we'll be able to put them together. Phenol, again, not so reliable, broad range. Carboxylic acid now, all the way downfield. That's probably the furthest downfield you will see, and that's because you're on a very powerful electron withdrawing group, and that signal is de-shielded to that extent. We will talk about C13 later in the week, and I'll do a similar sort of definition run so that we can see where these things come from. But those numbers now need to be understood, not necessarily memorized, but become familiar with them. Brianna? How would you tell, how would you tell, what technique would you use to work out if you had chlorine or bromine in a molecule? Mass spec. So that's exactly where we're going, is putting it all together, which is make or break for a lot of people. You put 5 pieces of data in front of people, and some people just lose it. They completely freeze, and they can't do this. And that's an indication that maybe this isn't for you. Other people will sit there and go, great, this is fun. I can put the, Kyle's like, yes, come on. You put the pieces together, maybe you should be in science, maybe you should be in medicine, something like that, because that's what we do. Now, to get this started, we're going to talk about very simple spectra with only one signal. And then we'll build it up. By the end of today, we should be into multiple signals, and we should be into multiplets, talking about where the things show and also maybe what shape they should be. I have here a very simple molecule, ethane. And at the top here, I have an idea of here's where ethane shows. The CH3 groups are the same. They should have one signal. And there's no splitting in this for a reason that will become apparent in a second. 2.2 should be within your range of N neighbor from your sheet. 3.2 should be in the range for your O neighbor. And then fluorine, 4.3, probably isn't on that chart, but this trend will be obvious. What is changing in this series? What's the obvious thing that's changing that will affect this outcome? Electronegativity is changing, right? So there's a pattern here where the more electronegative group tends to pull the signal downfield. Now, that's called de-shielding. And the idea is, if you think about the bonds here, in a situation like ethane, you simply have carbons and hydrogens. So what's the electronegativity of C? 2.5. What about H? 2.1. They're not that different, right? Well, we've also got to remember that not only are nuclei potentially magnetic, but electrons are magnetic. They're spinning charges, so they should have a magnetic field. And it will be the different magnetic fields experienced by each of these atoms that causes the difference in chemical shift. So if I asked you, thinking about these bonds that are bonding to C2H, where is the electron density there? Closer to H, closer to C, or about equal? It's about equal. It's not too different, right? Compare that to the left. Where will the electrons be in the bonds between the C and the H when you have an N present? Think about the structure of the molecule. N, C, H. What effect will that N have on the electron density in these bonds? Will it pull it closer to C or push it away from C? Close to the C. It'll pull it towards itself and then inherently, or obviously towards C also. So that'll make a little bit of a difference. We're pulling away from H. So de-shielding is pulling electron density away from a proton, and the manifestation of that on the graph is to send it downfield, in other words, to the left. So I am speaking a completely different language now. Yes? This is very different, so we've got to keep up. So here we go. The first one is the simple alkyl group, which is shown as R3CH on your graph or your chart right there, and that shows up to the right. So 0.91 ppm, something like that. You can always tell that you have alkyl groups by looking up to the right of the spectrum. In this example, we have an N neighbor. The N neighbor is pulling electron density away from the neighboring C, which will then pull electron density away from the H, and that means that this proton is going to be de-shielded compared to the external magnetic field, and the manifestation of that is a shift downfield. 2.2 ppm should be in your range there, should be in the approximate ranges in terms of where these things will show. It is going to be consistent, I think. If we go to an O neighbor, we now see the signal at 3.2, and if you see a signal there, you think you practice these things, you think you have an O neighbor. You have a chance to start the problem. Maybe it's an ether molecule, maybe it's an ester molecule, things that contain those types of bonds. Now, going further downfield, we don't see much of fluorine, but there's to show that it's consistent. So if you put a fluorine on a molecule, you see 4.3 ppm. Very simple signals, but consistent now. Electronegativity plays a large role in where the chemical shift will appear. Okay? So keep an eye on that, Michael. Not there yet. Give me a few slides. Not there yet. Now, if you move further downfield to the left, on your chart there, you'll see that benzene and double bonds tend to show up to the left. You have alkenes that show up at 5-ish, you have alkanes that show up at 1, and you have benzene all the way down at 7. Now, you don't even know to worry about the physics of this. Okay, it's all to do with the effect of the pi cloud and how that affects the external magnetic field and the interaction with it. What you are concerned with is the manifestation on the graph. Where does it show, and how can I use that to work out problems? So if we see something around 7, chances are it's one of these ARH, which is defined on your chart there. It'll be a benzene ring of some kind. By the end of this week, we ought to be able to work out, is it mono-substituted, di-substituted, is it 1,2 substituted, 1,3, 1,4, stuff like that, based on symmetry ideas. So an awful lot of stuff to come now. This idea of the CH alkene, again, consistent. If you see something at 5, it's probably an alkene, or it could be something with an oxygen, or maybe an oxygen next to a nitrogen, something like that, where we add the pieces together. So basically, that's the playing field. Now, you go further downfield in a minute, we'll start talking about aldehydes and stuff like that. But now we've got some patterns, some consistencies. All the way to the left, for a CH bond, you're looking at alkyl. Halfway down the spectrum, 5.3, probably an alkene. And then further down at about 7, you're looking at a benzene ring, or an aromatic type of system. They are consistent, and from now on, from today, you should be happy with that. Okay, moving on. Now, fortunately, the graphs can be much more complicated, because much more complicated means much more information. And you must see now that each different type of proton in a molecule will have its individual resonance. It will have an individual signal in that spectrum. And we can start off making it more complicated by looking at a simple system like that. Is there any symmetry in that system? No, right? There isn't much of any symmetry. Maybe around here, maybe this is the same as this. But in terms of global symmetry, there isn't any. That system is not symmetrical. So I can now start to think about where these things will show. What type of proton are they at the top from your chart? Are they alkyl? Are they alkene? Are they next to N? Are they a banana? What are they? They are alkyl. So where should they show? Up here. Okay, there's your alkyl type protons. The size of the signal will mean something fairly soon in terms of being able to use that to work out how many of those types that you have. What type of protons are these next to the carbonyl? Alpha to CO, what do they show on the chart? Round 2, 2.1. Okay, there's 2.5. That's in that range. What about this last type? What type are they? N neighbor. All right, N neighbor, 3, and that's exactly where they show. Now, what are these little things down at 7? What do they belong to? The protons on the benzene ring, of which there are 3 of them, and they're all different because there's no symmetry here. And you can see within that sort of 7, 7.5 range, you do see 3 signals. Yep, it's reliable. So now we can start very quickly to look at more complicated spectra before we move into the splitting patterns. Kyle. Yes, you would. And if you're fortunate enough to have a multi-probe nucleus, a multi-nucleus probe, you could do fluorine, you could do boron, you can do nitrogen, you can do phosphorus, anything that's magnetically active. We're going to concentrate on carbon and hydrogen in the class. So now we can start talking about actually putting a spectrum together. We can talk about where you might expect these things to show. And this is what we'll do in recitation, is actually practice drawing these things. I will ask you on the next exam to draw a spectrum. I think it's a good way of making sure that people know what they're doing, making sure they're learning what's going on. Yeah, so make sure we can do that. These are just the basic definitions to put them together with your sheet, and you should see now that it's all based on that. So don't lose this. If you want another copy, it's on the website. The answer key for the exam from last Friday is going to be on the website this afternoon. I'll put it in the, what's it called, the course pack. I'll add the exam answer key for the course pack. Go find it, and then if you need to ask me questions, do so. Okay, now, your job is to work out very quickly what type of proton you're dealing with. You can look here at a cyclohexane. What type of protons? They are obviously alkyl protons. Even though it's a cyclohexane and a different shape to ethane, they show in the same place. This is up around 1 ppm, in this case 1.5. And we might argue, okay, secondary carbon, maybe you've got 2 carbons attached, a little bit more electronegativity, maybe that's why it shifts downfield a little bit. So now we can see that that's consistent. And if you put the O neighbor together here, the relationship here, what's the relationship between that proton and that proton? Same, that's why you only see one signal. So again, the symmetry idea is important. We've got a little different situation here. Very quickly, it gets more complicated. Why 2 signals? 2 types of hydrogen is the way we say it, right? There are 2 types of hydrogen. The red hydrogens here and the red hydrogens here are equivalent through symmetry, and they will show in one place as one signal. Now over here, we've got a second type of hydrogen. Why, or even go back before that. Which signal is this one downfield? The blue or the red? Blue. Why is it so far downfield? It's between 2 oxygens. It's feeling the effect of both oxygens. Now, be very careful. Listen to this and make a note of it. You cannot simply add chemical shifts together. You cannot add the 2 chemical shifts together for O neighbor and get the answer. It doesn't work like that. They don't go that far downfield. So if your chemical shift is 3.5 for O neighbor and you double it, that's 7. That's way too far downfield. It will be downfield, but not as much as twice. So now we'll talk about the size of this thing. This seems to be smaller. This seems to be bigger. That will be important in a second. But so far, the chemical shifts, where these things show, is logical based on things like electronegativity. Anybody out there? And Alessandra Volpe. Anything to say? No. Just give me my exam back. Pierce. Experience. Practice. That's exactly right. It's very much like playing a violin. Do you ever play a violin? Did you? Now, you must be good at putting your fingers in the right place to actually get the right sound. I'm awful. Right? One of those instruments that doesn't have a fretboard, it doesn't have exact places where you put your, and it's not tuned like that. This is exactly like that. It's through experience and practice and you know, playing by ear. So practice. Now, this is a little bit different because this contains an aldehyde. What other technique would help you get started on whether you have an aldehyde in the molecule or not? IR, where would the signal show for the carbonyl? About 1700, right? That's something that should be with you from already. But now we can see a sort of a unique signal, a giveaway, down at 10. Why is it so far downfield? Well, let's think about a resonance structure for this benzene ring. If I split that carbonyl and think about its electronic properties, we've seen this and we'll see a lot more of it in the future. That carbon is very, very positive. In fact, it almost looks like a resonance stabilized carbocation. So that is very deshielded. The proton on it is feeling the effect of this highly electronegative carbon next to a highly electronegative oxygen. And that shows on the graph by being way downfield. And if you see something at 10, and in the infrared spectrum you see a carbonyl at 1700 or something like that, that's an aldehyde. Definitely an aldehyde. So with that in mind, we're seeing here 2 sets of signals. One is the aldehyde. These signals are for the benzene ring. But they seem to be shifted down towards 8. Any ideas why in that molecule those protons here should be further away from 7? Deshielded. What's the effect of the aldehyde? Electron withdrawing or electron donating? Electron withdrawing, right? So those protons are losing electron density, deshielded, and sent down to the left a little bit. And that will be very helpful when you have little decisions to make on the actual final structure of a compound. Michael? No, it's more to do, we haven't really defined benzene yet, but it's all to do with the proximity of the carbonyl to those protons, and then less so to these protons, and that proton is exposed by resonance effects. We haven't spent a lot of time on resonance and benzene yet, but we will, and show why those things are that further downfield. And by the time we get to the next exam, you'll be able to do this with benzene, and it's lots of fun. Carboxylic acid, Any indicators as to how you would know it's a carboxylic acid if you didn't have an NMR spectrometer? IR, or you could do a test. You could do what you did in freshman lab, which I think was the working out the pKa of this thing. I think you did that. You find it's about 5. And then here we see further downfield, 11. It's about as far as we go. That's super deshielded because the proton is on oxygen. Now, why so much further downfield than OH in an alcohol? I think it's got a lot to do with the fact that these electrons are pushed into that carbonyl. So that's a very positive oxygen, and therefore that proton is so far downfield, which you can't do with a regular alcohol. So simple ideas and simple effects which give you a handle on where to expect these signals. For those in recitation, next week we'll have our first sit-down quiz. It'll be one of these problems, putting it all together. Here's a bunch of spectra, what's the molecule? And if you practiced on those things, you can be out in 5 minutes. And people could be sat there for 3 days and still not get it. That's just the nature of the game. Okay, now, we have talked about chemical shift, where the signals show. That's probably the most important thing. Now we have to talk about the size of the signals, the intensity of the signals. This is quite reliable. It turns out if you look at these signals, and the program I use to make these is quite nice because it tells you that's a curve, right? When this has been drawn, the pen has gone across the screen and it's gone up and then it's come down. So there is an area under that curve, and you can measure the area underneath that curve all the way down to the baseline. And it turns out, fortunately, that the area under the curve gives you a ratio of the number of each proton you have. So that's where the number comes from. This number here, and this little digital integrator here is showing you that if you integrate underneath that, and that's all that means, is measure the area underneath that, that turns out to be 1, and you can, put it as 1 on the computer, and then everything else goes relative to it. And if you went with that computer pen and you went across the screen further from down here, which is starting there and ending there, the ratio would be 5, 1 to 5. But it's a ratio. Keep an idea of the fact that it's a ratio. So 1 to 5 could also mean 2 to 10, right? 1 to 5 tells you in this molecule that you have a 1 to 5 ratio. What would the ratio be? If your integrator was good enough to be able to integrate that signal and then separate those two signals, what would my numbers be here and here and here? 2 to 1 to 2, which is 2 to 1 to 2. That's where this comes in very handy. Now, if you're as old as I am, which I'm starting to feel very old, we first learned this on old continuous wave instruments in which the pen moved across a piece of paper and you had to watch it resonate. The pen went up and down and you got the signal. And the way we'd work out integration is to take the piece of paper and cut out the signals. And then you would weigh those signals, those pieces of paper, and then you'd get a relative weights. And those relative weights would then give you the integration. But no, nowadays everything's digital, right? So you just do this in seconds. The experiments run for you, it's shown on the screen, and you just print it out. Everything's worked out for you. But this now is a ratio of that type of proton to these types of protons. That's one of the 4 or 5 very valuable pieces of information you can get from NMR spectra. Chemical shift is very important, and now this idea of integration is important. It is the area under the curves, and the area under those curves is now going to be a ratio of how many of those types of protons that you have. Mr. Homan. I will give them to you, and I will explain as we work towards the end of this chapter how I will present the information. At this stage, I'll give you both the graph and the numbers underneath. So if you can't read the graph very carefully or very nicely, you've got the numbers underneath, and that will include integration and a whole bunch of other stuff. Okay, there's a lot of information here to be able to pull out. So here again, we can see a spectrum that has, in that molecule, I think 3 types of proton. This methyl group is different to this one, is different to the CH2. Why are the 2 methyl groups different? What type are they? What type is this on the left? Simple alkyl, right? With no O neighbor. It's too far away. What about this methyl group on the right? What type is that? O neighbor, because it's an ether, it's part of that system. And what about the CH2 right here? What type? O neighbor. So in this example, we can see now some shape. Shape don't worry about just yet, but we can certainly see chemical shift based on what type they are, based on electronegativity ideas and their proximity to the electronegative atom. But we can also see the graphs. We can also see the integration. This one down here apparently is worth 2, that's worth 3, and that's worth 3 if you measured underneath those curves. So which signal is this? If I label this 1, 2, 3, which signal is this to the right? 1, number 1, all the way to the right. What about this one here, this line that's quite large? It's worth 3 protons, so which one is it? 3, it's the methyl group. And then down here is the CH2 group. You will have that information, but you won't have a structure in front of you. So you can see where this is going. This is getting very much more complicated. You're going to have to practice, like, work on this stuff to be able to master it, because it will be a significant amount of the next test and the final. And we use this stuff all the way through because this is how we know what we do. This is how we know the answers. Everybody happy? Mrs. Holman, you happy? You lot at the back? It's wasting your lives away? Okay. Other examples here, more complicated signals. We can see a benzene system. Now I'm going to mention this now, and then we'll come back to it because we haven't done any benzene chemistry yet. Look how clean that pattern is. Those protons down there, one of the signals belongs to this set of protons, and the other signal belongs to this set of protons. Why is it so nice and tidy? There are differences in electron environments, but you've got 4 protons. Why do you only see 2 signals? Symmetry. Symmetry. And when we get to C13 by the end of the week, symmetry is killer. Symmetry is everything. That molecule is symmetrical, and so you only expect to see the protons here, maybe next to the electron withdrawing group, maybe that one, and this one further away, maybe that signal. But that clean benzene ring region tells you a lot about symmetry. Tells you what type of pattern you have on the benzene system. But again, without overdoing this, 2 hydrogens for those 2 sets, 2 hydrogens for the CH2 group, 3 hydrogens for the methyl group, which one is probably alpha to the carbonyl, and then this signal here, 1.3-ish for the methyl group up there. Very quickly today, we're looking at complex spectra. Not wasting any time with this stuff. So in about 5 minutes, and I'll give you a test back. Multiplicity. I ought to start this today and then get on it on Wednesday. This is basically Wednesday's class. What do the shapes mean? Why do we see shapes in these signals? And the answer is because the protons will talk to neighbors. The neighboring protons will have an effect on the shape of the proton next door. It's all about neighbors. So we'll start off very simple. I'll get this going, and then you can read about it and come back on Wednesday and we'll crack into it. The red hydrogens, what type are they? What type from your chart? Alkyl. So this should be the CH3 group. But now the CH3 group is made up of 2 lines. It is split into what we call a doublet. That line and that signal shape will tell you an awful lot. Then this proton here must be this one here, and that's the CH group. The reason it's so far downfield, it's much further than just 1 chlorine, is because it's next to 2 chlorines. We're past that. We're now talking about signal shape. So the signal shape here, I'm going to define this as a doublet. Okay? And this signal shape down here seems to have 4 lines in it. And very quickly, you will think of this as a quartet. Now I argue anybody who can read music should be able to do this stuff. Anybody who can speak a different language that has a different alphabet should be able to do this stuff in their sleep. There's nothing tricky to it if you learn the parameters. So all of a sudden we are seeing the fact that that doublet, right, that signal right there is down here. It's a quartet, and that's because it has 3 neighbors. And we're going to say that if n is 3, number of neighbors is 3, n plus 1 is 4, and that gives you an idea that the signal should have 4 lines in it. There is a mathematical explanation coming up in a second as to why that, or maybe Wednesday as to why that shape is as it is. But over here, for the methyl group, how many neighbors? How many neighbors do the red hydrogens have? Just the 1. So what's n plus 1? 2. For this example, n equals 1. So n plus 1 equals 2, and that is a doublet. You see singlets and doublets and triplets and quartets and quintets and sextets and septets and octets, and then doublets of doublets and doublets of doublets of triplets. And it's a language in itself. So, here we go. This molecule, slightly different. I changed it into CH3, CH2, Br. Chemical shifts are up to you. You have red protons, which are simple alkyl, then you have Br neighbor further downfield. That's why they show down there. In terms of the shape, this signal is for the CH2 group. And it is not because it is a CH2 group that it has 4 lines in the signal. It's got nothing to do with that. It is to do with how many neighbors you have. So in this example, there's the CH2 group. How many neighbors do the blue hydrogens have? 3. 3 plus 1, 4. Quartet. On the other side, on the right-hand side of the spectrum, we have the signal for the CH3 group. How many neighbors? 2. That one and that one. And n plus 1 there gives you 3, which is a triplet. So I'm going to jump ahead to that slide. and then go back and I'll rehash that on Wednesday. Look at those names. Look at them and know them. There is no such thing as a tet. Yeah? They are defined names that will be used, and if you go into pharmacy or medicine or anything like that, you probably will see this in the future. So know those names and know them properly, so that we're speaking the language properly. And Wednesday will just fly, because I'm going to talk about how this works in terms of where they come from, in terms of those shapes, in terms of the neighbors, in terms of how you can use this stuff, and very quickly start to do very complex spectra.